think math club meets this afternoon, and they're doing puzzles. 1:15. Just 1 second, friends.
Okay, let me get all the shit out of my pockets now, and then I'll be ready to go.
Enough. Alright, I don't think Kayla's, well, I know Kayla's not going to be here today. And maybe Michael will. Don't know. Figure it out. Let's just take a minute to check in and not do something for 2 to 3 minutes. Stop doing stuff. You do enough. You spend your whole damn day doing stuff. Take a couple minutes, turn off the switch. Starting now by just tuning in to the sounds in the room. You could take a brief moment to look for who is listening. Where's the listener? Just briefly. I don't want a prolonged effort at that. Otherwise, just let all this sound impinge. Notice that you aren't doing any of it. It is just happening. Let's come back together. Do some real analysis. So that whole thing of looking for, you can do this like throughout your day, and it's really good practice. It's something I actually do like throughout the day whenever I'm mindful enough to do it. But look for who is doing whatever it is you're doing. And it sounds weird, and it sounds possibly stupid, but you can totally turn your experience inside out in a flash by doing this. I mean, when you think about it, the thing you're experiencing right now is completely in your head. All of this is completely in our heads. This is like VR right now. And you might find some interesting things out about nature of reality, or at least a new way of looking at it, for sure. And you get a sense of peace, too, from doing this. Hopefully not anxiety. Questions on the homework? Sounds like a funny question. We have a homework, right? Yeah. Any questions on that? No, you got anything? next Monday from you. Because it looks like Wednesday might be a little push at this point. 0 questions and so forth. Which might be cool. You might totally just be all over this stuff. Noah, you good?
Yeah.
Okay, cool. Yeah, don't force a question. You don't have to. You don't have to do that. Okay, so quick question for you, little fake quiz. Can you define continuity? Can you do it in one way? If you can get one down, can you give me an alternate definition of continuity? What do you got in your head? And if you don't have anything in your head, that's cool. Listen to the sounds in the room. Bad news for everybody. Hey, Michael, good morning. Just doing a fake quiz. Anybody got anything for me? I saw you writing something, Noah.
If the limit exists, it is the same at a point as the point. So limit of x of c equals f of c.
Got it. Cool. That's good. I like that one. Nice. Hella good. Yep. Any others? Got another one? Okay. How about this one we didn't really talk about, but it's in the book, and it's the delta epsilon. So let's actually talk about the delta epsilon. For all epsilon greater than 0, there exists a delta greater than 0, and this is essentially this in a mathy way. There exists this delta, so call response. Remember, just really quickly, this is C, and this is f of C. I'm going to be given an epsilon neighborhood around there, and if this thing is continuous, I can always find a delta neighborhood around C so that the function lands inside that little box right there. And so there exists this delta such that when x minus c is less than delta, now notice when it's just the limit existing, when it's just this limit equals something, there's a greater than 0 here. But in the continuity definition, x can equal c because f of x is defined for continuity. So we take off that 0 less than part on the left. When this happens, we have f of x minus f of c less than epsilon. There's a lot in there. Writing this says I know that f of c is defined. And then this can be said in a really beautiful way using our neighborhood notation. So for all epsilon neighborhoods around f of c. That. There exists a delta neighborhood around c. Watch how beautiful this is, such that f of v delta of c is contained in v epsilon f of c. This is probably one of my favorite ones right here. Because this really says what that says, and of course what that says as well, but in a very intuitive way. You give me the v epsilon up here, I can find the v delta around c such that f of all those points lands inside there. And that's all that says. But it's something about it I feel like is super intuitive and easier to handle, like emotionally, mathematically, and all sorts of stuff. And I want to give you a fourth one today. And this is a special problem in the book. And we kind of have to have a special situation for it. But this is my favorite continuity characterization of all. If we suppose that f is defined on all of R, so notice, remove it from a restricted domain to just everything is cool. It really makes life better for this. We could do this, but then we have to talk about relative topologies and relative open sets, and it's just like, not now. So suppose f is as happy as a function can be if f inverse of u is open for each open set u in R. This is a weird one. Then f is continuous. That's the most elegant definition of all, for sure. Really clean, really powerful, also really weird. But I'm going to show you that it's actually the same as the stuff we got over here. And in the process, kind of review how this all works. So here's our problem. Show, and this is probably an if and only if, actually. So sorry, you could change this. We could put a if and only if there. Because those are the same thing, so apologies for that. That is a biconditional. So let's do a proof. Suppose that f inverse of u is open for all open subsets of R. And we're going to show that means f is continuous. And we're going to go with characterization 3. It's going to make a lot of sense. And so I think you'll start seeing this come together as we go through here. Let's go proof. Oh, wait, I already got proof. There's one proof. That's enough. So let's just draw a picture of what this means. So draw ye old arbitrary. That's a little too vertical for a function. So here's y equals f of x. And then over here is some u. Now I'm making u look like one of these guys, like an epsilon neighborhood, but it's an open set. So it could be arbitrary unions of open sets. Who knows? It's a bunch of, in the end, it's a bunch of open intervals union together. We haven't really said that, but like every open set in R is just a bunch of open intervals combined in some way. So I've got this open set U, maybe a little more complicated than a simple neighborhood. And I know that if I pull, so the inverse image means take this back, come down here, and then do that for each one of these. That's a pretty shitty job I'm doing there. But this down here, this pullback, I'm going to get rid of that one so I don't have to draw another set of lines. But this is f inverse of u. And let me make that official. So for a set u, f inverse of u is a new set is the set of all x such that f of x is an element of U. It's all the stuff that gets sent into U. Anything possible that could do that is in that set. Let me show you a really quick example here too of a slightly more complicated function. Let's just say we had x squared. And I asked you to find, here's U, and I asked for f inverse of U. That's actually going to be a couple sets because this thing is 2 to 1. So f inverse is actually these two intervals like this. These guys comprise, sorry Mike, I'll get out of your way in just a second. I think I'm right smack dab in the middle. So it could actually produce more than one open thing from one open thing. Or, okay, I don't know why, I'm just gonna keep, maybe I'm belaboring the point, but that sounds like something I would do, so I'm gonna keep doing it. Let's say we had a sine curve, right? And I asked you to find the inverse image of that. How many of those are there? Infinitely many, right? So like this, and we don't even want to draw them out because it just starts to be a drag, but anything, and that's like, look, it's a shitty graph on top of it. But like here's one of the inverses, and then over here, here's another, and then here's another over here. And so that's just infinitely many copies here. Anyway, I just wanted to kind of make sure that we understood this idea of f inverse as a set, not a function. This isn't an inverse function. That's not an inverse function because inverse functions don't exist for functions that aren't one-to-one. So this is a more abstract thing. If I asked you to find the inverse function of this, you couldn't. It has to be one-to-one. So this is just set stuff. All right, so let's show it's continuous at an arbitrary C. So take C in R, that's our whole domain, so that's good. So I'm going to draw a picture again. With this continuity stuff, I think pictures are essential. So here's C, and then f of C would be up here. So I'm going to pick an epsilon neighborhood around f of C and show that I can produce this delta. Take C and consider V epsilon f of C, and of course epsilon is a happy positive number there. That wouldn't make sense otherwise. Consider this, so now I come to that. Okay, awesome. So there's the plus epsilon, there's the minus epsilon. So this is an open set, right? That's open. That's, I mean, it's like one of our primal open sets. It's an open interval. So this is open, so if I take f inverse of that, if I pull that back, and you might want to draw some kind of fake f here. So if I pull that back, then I've got f inverse of v epsilon of f of c. There's going to be a lot of parentheses. It's going to look complicated, but it's not as complicated as it seems. So I pull that back. I know that this must be open. So this is open, this must be open by hypothesis. So consider that. Then by hypothesis, f inverse of v epsilon of f of c is open. Cool. And C must be a point in that set. By construction, C is in here, is open, and contains C. Take a minute and just convince yourself that this is all righteous. Because right now it's probably starting to sound like I'm just rambling. Just blah, 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 blah. Charlie Brown, real analysis. So take a moment, get with it. And let me know if there's any questions. produce a delta neighborhood around this C that maps into that upper neighborhood. How can I do that? Any suggestions on how we could do that? So I've got, let's look at the picture, and let's actually kind of draw this down here. So here's the x-axis, and then here is F inverse of V epsilon of F of C, and somewhere in there there's C. How do I know I can make a little neighborhood around C that's inside there? What, Michael, yes sir?
Do the thing we've done before, subtract the distance from the left and the right, and see which one is the minimum.
Yeah, that's cool. We could, absolutely, we could do a construction way, but how do I know that distance isn't 0?
Because it's open.
Because it's open. So the two of these, awesome, perfect. So your two ideas together, the fact that this set is open by hypothesis means that I can fit a little neighborhood inside here. And I could get really precise about it, like Michael was saying. We could say delta is the minimum of, you know, like half these two distances here. But we don't necessarily have to go there. We just know that because this is open and C is inside of it, so since it is open, there exists a V delta around C completely contained inside there. Completely in there, right? That's what open means. There's always space around me. I got, no matter where I'm at in that set, there's room to the left and right. So, got this. Now, this just means, like, think about the definition of F inverse. This thing just means that F of V delta of C is contained in V epsilon of F of C. And if you want to think about it in like maybe a not 100% right way, I'm applying F to both sides of this. Maybe that actually is totally legit. So apply F to this side, apply F to this side, the F undoes the F inverse. And we got this, and that is characterization 3. So by characterization 3, F is continuous at x equals at C. That's one side. Let's do the other side. I'm going to make you do more of it. Or I'm going to try to make you do more of it. I'm going to implore you to do more of it. So now we're going to work with this definition and prove that F inverse of U is open for each U. So now assume, so this is the other direction, F is continuous on R. I would use this characterization right here. We're going to take a U, subset of R, that is open. I want to show that F inverse of U is open. Take a minute. Can you pull this together? So you've got to produce a neighborhood in there, right? So take a point that's in there, show you can produce a neighborhood that's in there, and this is going to be your friend. Just a little bit of suffering right now. Let's suffer together. I will get you started. So. To show there exists V delta X. Okay.
I forgot.
Okay. I think they got the argument. Not yet? No? Okay, that's all good. It's the struggle. Struggle is worth it. No, okay. Should I give a little hint? Nudge. I'm gonna give a nudge. Take your X in the inverse image. This is what I want to show is open. I don't know anything about it. I have to show it's open. Right? So I do know this is open. So I have to go here to get information to bring back here, because this is where the information is stored. So I come up here and I say, okay, this is open. So around f of c, I can definitely find a little neighborhood of, let's say, size epsilon that fits in there. Right? So we could say since, and I'll just get you going, since u is open, there exists a v epsilon around f of c, which is in there. So actually, let's put a note. Note if, or I should say x here, sorry, because I picked x. If x is in f inverse of u, f of x is in u, just to make that note. It's obvious from the picture, but we want to make that note here. Since u is open, there's this epsilon neighborhood that's in there. Well, what I have, now I've got to produce a v delta neighborhood. How can I do that? Oh, exists v delta contained inside u. That's the rest of the statement that I should have said there. This is what we know. This is our hypothesis. Any notions? What do you think, Noah?
Since f of x is continuous, we can find a epsilon neighborhood around x. That is in v epsilon.
Yes, so since this is open, I've got the v epsilon, yep. Now how do I get my delta?
Well, because it's continuous, you have a delta, right?
Yeah, so yes, because of continuity, I automatically get that delta.
Yeah.
Yes, yeah, Michael, were you gonna say something?
Is it using the, I guess use nice word, the pre-images of f of c plus epsilon and f of c minus epsilon since they're in the output set?
Oh, that could be potentially dangerous. I'll show you why in a picture. But look, so I've got V epsilon up here, right? I've got an open set up here. By continuity, there exists a delta neighborhood down here, so that this all maps inside of there. Since this is already inside of U, this must be inside of F inverse of U. Let me write that out. So there exists this. By continuity, there exists a V delta around X such that F of V delta of X is contained in this V epsilon neighborhood. I.e., and this is contained in U. So check this out. Let's summarize that. I.e., F of V delta of X is contained inside of U. Apply F inverse to each of these. So F inverse of this side, or just saying this is another way of saying this statement here is the same as that statement. And so now I've got a delta neighborhood inside of F inverse of U, and I produced that for an arbitrary X inside there. So you could just follow this process for any X in F inverse of U. You go up here, you get your epsilon neighborhood, you pull it back by continuity to get your delta neighborhood. That's the game. And I think that's just kind of cool. So this implies F inverse of U is open. Done. I find that joyous. Your mileage may vary. I think your mileage does vary. All right, let's get more concrete. We're still doing continuity, so there's no escaping continuity this week. Not at all. Are there any questions here before I erase? Start erasing slowly. So, let's take a look at something. Let's say this got f of x equals x. Is that happy, right? Yay. Y equals x. Okay, that's cool. There we go. Woohoo! If I pick point C, what you see here, it looks a little more fixed, and here's, well, that's going to be C also, right? Because y equals x. And if I pick an epsilon neighborhood around this, what's a good delta response down here so that all of this stuff lands over there? So delta equals what is going to work? Epsilon. Is that clear? Okay, cool. I'm getting a lot more head nods on this shit. This is good. Exciting. So look here. Delta equals epsilon works. And in fact, is that the only delta that works? Is there only one delta for, no, any smaller one, right, is going to work as well. So delta equals epsilon or smaller works. Cool. Let's get another one up. So I really want to explore this relationship between, oh, by the way, let's roll with this. We just bought something really awesome. We just need to polish it up and put it together. It's IKEA. We got to put this shit together. So this says, so look, x is continuous. So f of x equals x is continuous. And I know that the product of continuous functions is continuous. So f of x times f of x is also continuous. And I forget what theorem it is. There's a theorem that tells us all this stuff. So any product of those is going to be continuous. So if I take f of x, bootstrap my way up to n copies, multiplied together, that's continuous. I know that linear combinations of functions that are continuous are still continuous. So now I've got all polynomials are continuous. And then we don't have to pay for that ever again. So look, from here, all linear combos of continuous things are continuous. So, P of x equals A naught plus A1x all the way up to A sub n x sub n is continuous. Yay, now we never have to prove polynomials are continuous again. We own that now, right? It's got an NFT, we own that. This is more useful than an NFT. Okay, so got that, and we also know that this is continuous. F of x over g of x is continuous if f and g are continuous and g of x is not equal to 0, because that's obviously a bad move, right? So this is going to be continuous if that happens. So p of x over q of x, rational function. It's a ratio of polynomials. Is continuous on its domain, everywhere that q of x doesn't equal 0. And there's a couple nice results. On its domain, i.e. where q of x is non-zero. Cool, so from this simple observation, we just bought a bunch of functions. Really nice. We have to be careful with this, though. Don't assume that infinite series are continuous, because they're not. Because I can crank out an infinite series of things that are pretty bad. So this is only for finite sums. Let me ask you this. How about this function? Really quick, let's say I've got f of x equals 1/2 x. This is c, and I've got an epsilon call over here. What is the appropriate delta response? So take a moment, I've got to run to the restroom. But what is delta equal? What will work? And pick the largest. There's infinitely many. Bless you. It's so nice to not be sick. Getting on here for a purpose, not to check my NFTs. Which I now own some. I've sold one. I sold one NFT, made 25 cents.
Congratulations.
Thank you.
You gotta get that sign on soon.
What's What's that?
You gotta get your side hustle.
You got to, man. Oh shit, well, that's not gonna work. So now we wait for the gophers to reply. We haven't had lettuce yet today. So, what's the appropriate response in terms of epsilon? What is gonna work here? 2 epsilon is gonna work. Does that make sense? Do you see how that works? Because this is just a nice constant line. It scales by a factor of 2 back this way, and by a factor of 1/2 up this way. So if I take any neighborhood down here that's just 2 epsilon, that's gonna work. That whole thing is gonna map into this epsilon neighborhood up here. So that works really nice for lines, but what I wanna show you is a parabola. Do we also agree that the same delta would work no matter where I'm at? Does that seem reasonable? That no matter where I do this delta response works everywhere because of the constant slope of that line, and it's very predictable. But let's take a look here. Let's see if we can get this to work. Should have done this ahead of time. Does that thing look like it's on?
The green light is blinking.
Hey, that's happy. I'm going to Desmos, because I haven't been there yet today. Ooh, I know what I want. Desmos Delta. Cool. Oh, good. Good. I can show you this. You're gonna like it. No, would you please get the lights? That would be very helpful. Thank you so much. Maybe even just this front one. Yeah, that's great. That's beautiful. Unless you like it romantic in the back there too. Just feel free. So, okay, let's take a look. Where is my function here? All right, so let's look at what we just did here, and we can really see this in action. So there's 2x, and let me get in here. Grab it. So notice that here, bless you, we are at the point x equals 1, output equals 2, bless you again. So right now, the delta response is not appropriate. I need to shrink it because look, there's parts of this function in this delta range that don't fall into that horizontal strip. So let's shrink delta down. So epsilon here is 0.5. Notice how not until I get to 0.25 are we kosher. Oh God. Grandpa. All right, so there. So it turns green as a really cool feature of this when we actually have the appropriate delta response. And of course, any delta smaller than that is also going to work, but the minute I go over that, it blows it. This delta is going to work regardless of the point. Do they have a place where we can shift the point? Let's see. Oh yeah, watch. Let's check. Oh God, damn, Desmos is awesome. Look at that. No matter where we're at, the same delta works for epsilon. So there's a uniformity there. But now the minute I move that 2 up to an exponent, well, we have to kind of play here because that we shouldn't expect that response to work. Let's move back to here. Okay, oh look. So now it depends on where I'm at for that setup to work. Down here, we can blow this all up. Very happy to have epsilon at 1/2, and then delta can be, wow, delta can be lots of things. Look, it can grow all the way up. Let's see, how big can delta get here? Okay, so that blew it, so I come back a little bit. So that's the maximum delta at this point, and our current point is 0.4 for that fixed epsilon. We're never going to change epsilon from 0.5 for this demo. So if I take the point where I'm doing this limit, and and I start shifting to the right, instantly, look, that delta doesn't work anymore. It does work for all these in here, but the minute I get out of that range, it doesn't work. Okay, well, let's adjust it. So come down, I go, okay, I gotta tweak delta a little bit until that turns green. Okay, cool. Well, there's a delta that works. Surely we're in the green from here on out. You can clearly see that's not gonna be the case, or hear that in my voice. So I come to my limit point and, oh look, oops. But if I come out here, oh God, it's terrible. So let's tweak it. We have to really shrink delta. Ooh. Notice that delta does work for all of these to the left. But the minute I set it for one, it doesn't work for larger magnitude x values. So the point I'm trying to make here is that for certain functions, for most functions, in fact, a fixed delta can't have a fixed epsilon can't have a fixed delta response. We have to look at where we're at, what the nature of the function is, to determine delta. So let me write, okay, I'm gonna get this up. That was, thank you, Regis Computer. That was like literally the most effective impromptu you have ever been. We thank you for your service. All right. Thank you, thank you. So, let me make the point that I want to make in words. In determining the delta response for a given epsilon, that's epsilon greater than 0, we need to consider the current location. Now, you're never going to want this. So delta is going to equal some function of epsilon. Actually, let's write it like this. So delta, here, let's put delta. Delta actually depends on the epsilon for sure. But it also depends on the x value. But this will be a pure epsilon expression in the end. So in other words, you just have to consider where you're at, and that's going to affect this relationship here, as we just saw with the x squared thing. If it isn't, we have a very wonderful thing. If one delta can work for a fixed epsilon, regardless of location, we have a stronger form of continuity. We have what's called uniform continuity. Let me get all official on this now. Let's get out some delta epsilon news. All right, so given, already need a new pen, given F, oh boy. Do you feel that too when you see it? I don't know, like as soon as I see the richness of that, it just really cranks my gears. I don't know, I was trying to think of like something to say that didn't sound creepy. Maybe that didn't work, I don't know. Given this, we say F is uniformly continuous on A. So uniform continuity also comes with a domain specification, so like a set as well. Where is this happening? If for all all epsilon greater than 0, then you expect that to be coming, right? If for all epsilon greater than 0, there exists a delta greater than 0 such that x minus y less than delta implies f of x minus f of y is less than epsilon. So check that out. And I'm like, is this where we wanted to go? More or less. Yeah, more or less. I just skipped a few things, that's all right. We'll hit them when we need them. So what I want you to notice here is that this y makes this look a lot more complicated, but compare it to, and I'm just gonna write this out, the classic continuity at a point C looks like this. You don't need to write this out under there maybe because I think it'll maybe foul up your notes. But this is the definition of continuity at C. And all this is saying is that C could be anything, any point Y inside there. So now, instead of this just being a fixed thing that we're given, it's just a Y that's inside of there. And this holds true for all X and Y inside of A. So it's just saying, no matter what my center is, Y, I've got continuity, and I've got the same delta that works for all epsilon that are fixed. Fixed your epsilon, doesn't matter where you're at, one delta will get the job done. All right, so that is uniform continuity. Let's see here. Maybe we should take a look at some things not being uniform and continuous. What is the negation of this? So this is uniform continuity. Can we just take a minute to brainstorm? What does it mean to say F is not uniformly continuous on A? What's the negation? Let me help on negating implications, just in case. That's how we negate an implication, which we have here, if then. Double-headed arrow to match up, or what we have there. Hopefully you occasionally think, man, I'm so glad I took logic and proof, right? We used to not have that class here, and then every upper level was just like a clusterfuck. Because no one knew how to prove anything, or logic, or, yeah. This class is so much more fun with you all being in the know. Somebody walk me through this. Come on, we can do this. Here's freaking P. Right? Here's freaking Q. So let's start at the front. How does a for all negate? There exists. Right? You just go through and every for all becomes a there exists, and every there exists becomes a for all. So there exists some epsilons, call it, say, epsilon naught, because it's fixed. So we've got some epsilon naught greater than 0, such that for all delta greater than 0, not this. So x minus y is less than delta, and there exists, right? So there exists x and y in A, such that, because I'm changing that for all to there exists, such that x minus y is less than delta, that's the p, but that doesn't happen. And f of x minus f of y is greater than or equal to the epsilon that's here. Let that register, make sure that you agree. You should agree, there's no like debate. That's another thing, so grateful to be a math teacher where we don't have open-ended discussions about things, where people have strong opinions that can't be validated one way or the other. Yay, math. No moral conundrums. Let me give you a nicer version of this. So we're going to take this and turn it into a sequential characterization. It'll be a lot easier to use. And I think that this is actually, let me get a site for you. This is there's uniform continuity. Oh, here. Yeah. So this is theorem 445. Essentially, theorem 445 says the following: F is not UC on set A in the reals if we can find an epsilon naught and two sequences in A, both the sequences are in A, such that, since over here epsilon is arbitrary, and I can always find 2 points that are less than any given epsilon. So imagine, or excuse me, any given delta. So imagine delta being this thing 1 over n, and we're letting delta shrink. And every time it shrinks, we pick a new x and y that satisfies this condition. So that means that x and y are shrinking together. They're getting closer and closer. And we can turn them into a sequence. So for each such n, choose x and y so that this happens, and you tick your way toward a sequence such that x sub n minus y sub n shrinks to 0, the distance between those two. But f of x sub n minus f of y sub n is fixed above epsilon naught. Those never get arbitrary close together. They're bounded away. And let's talk about how this works. So I think the book does x squared. Let's do something a little different. You can go read their example. You can read the proof of this. It's basically the thing I just outlined. But let's use this to show that x cubed is not uniformly continuous on R. Absolutely essential that I know the function and the domain, because I could make this uniformly continuous if I picked the right domain, which is kind of probably what we're going to talk about on Wednesday. All right, so here's x cubed. Yeah, nice to have a picture, feels good, feels comforting. If you don't know how to do this sequence, you could spend a long time just kind of flailing about looking for it. But remember how that example I worked with Desmos was. As we moved further and further out, a smaller delta response was required. And that you can see that that's the case, right? So take a look at like the inverse image of this versus the inverse image of the same strip down here, right? See how wide this is, see how narrow this is. Oh, I wish I had an undo button in life. right? Don't we all, I guess? But a smart board would be the next best thing. So what we're gonna do is we're gonna pick a couple sequences, X sub n and Y sub n, that are moving out this way, but getting closer together at the same time. And we're gonna show that it doesn't matter because F will still be bounded away from the output. F will still be, the output values of F will still be bounded away from 0. So let X sub n equal n, that's chill, and Y sub n equal n plus 1 over n. And here you can see that X sub n minus Y sub n is just 1 over n, and that shrinks to 0, so that's cool. So they're getting closer together and scooting right. So now what we have to do is analyze this. We need to find the epsilon naught such that f of x sub n minus f of y sub n is bounded below by that, no matter what n is. And the way to do this is scratch work, right? So let's just take a look at f of x sub n minus f of y sub n. So this is scratch. So that's going to equal n cubed minus n plus 1 over n cubed. And I, expand this out. That's n cubed plus 3n plus 3 over n plus 1 over n cubed. And you could check me out on that. I worked it out over the weekend. I'm pretty sure it's right. But notice how, so like for this one, you would have n squared and then a power of 1 over n, and then here you would have n and a 1 over n squared, right? So they cancel to give you those nice forms there. And then when I simplify, this is equal to negative 3n plus 3 over n plus 1 over n cubed. And so in absolute value, oh shit, well, we got, yes, thanks. I think you were seeing the same thing I was seeing, that, yes. That's good, because I wanted to take the absolute value of it. So note, absolute value of f of x sub n minus f of y sub n is just equal to, strip off the negatives, plus. And then this is always bigger than 3n, right? Yeah? And this, for n bigger than or equal to 1, is always bigger than or equal to 3. True? Yeah? So these two never get closer than 3 units, even though those points are shrinking together. And that seems shocking, but obviously true. That don't lie to us. So let epsilon naught equal 3, and we see that by theorem 445, that f is not UC on R. Yep. Let's just call that the end, yeah? I could do one more example, but I could also do it on Wednesday. Unless you really want to see it. You okay? All right, good. Thanks, everybody. It's only 5 minutes, and I'll walk around and talk to Michael. Yes.
We were supposed to do this, I think the video was put up from.
Oh, Wednesday's recording got barfed,
Oh, okay.
unfortunately. Yeah, so I'm sorry I didn't get that, but if you want reading, I can totally recommend some for you.
Okay, what did you want us to read?
Let's see, what should you read? Yeah, since we're all together, and you're like, I just put my notes away. Well, I'll send it out. I think that reading for next time wouldn't be the worst idea. You could probably read 4-4 if you wanted, and then 4-5 for fun. 4-5 is so tiny. It's the intermediate value theorem, but it's got some neat real life consequences as well. And we'll probably talk about that. We'll finish this up. We'll talk about 4-5 on Wednesday. Maybe come and you prepare to work a little bit, because we'll have a shorter lecture and then we'll work on stuff. The homework that's due in a week. Yeah? Okay, awesome. Thanks, friends. I think you'll probably be able to figure out what you missed, Michael. You're always really good at that. So, and if not, we'll be happy to talk to you about it. Sound good? Awesome. So you officially accepted the one?
Yeah.
Okay.
I took it a couple weeks ago because of the deadline thing.
Did anything kick in? Did they like ask somebody offer right after you accepted?
Yeah, the day
Oh
after.
God.
Rochester Institute of Technology. Yeah.
Oh, RIT. Wow.
Yeah.
That's okay.
Well, I heard from Dr. Gray that apparently the math department has heard of the one I was saying before. I'd never heard of that one before.
What was it?
Moravian University?
What was it? What?
Moravian University?
Oh, I know. I haven't. But
Well, because I said it, he's like, oh yeah, the math department really likes that one. And I'm like, huh.
I'm sure they're great. If you have an REU at your school, you've got stuff going on. So it doesn't matter. You did great, man. I'm so proud of you for getting that.
Yeah, that was crazy.
It was
The
crazy.
sequence of events that happened, yeah.
Yeah.
But we survived.
Absolutely.
Thank you.
Thank you. Diane. Hi, Trinity. Did you want to meet this week?
Yeah.
Okay, awesome. What would work good? I could do Thursday might be a little rough. Tuesday might be rough. Could we meet Thursday?
Thursday's fine.
Is that cool? Okay, awesome. I'll set up a Zoom time. So what's your schedule like on Thursdays?
I just have a class at 9:30.
Oh, okay.
45.
Oh, fantastic. So I was thinking maybe like around 11 or something.
Yeah,
That would
works.
work? Okay, awesome. I'll send you an official invite.
Do you have the homework? The ones that you.
Oh, no, maybe. Shit, I forgot all about those. Maybe I do. That's right, because that's what I was talking about. Good call. I wish I would have remembered. I think I do. This is them. Shit. Yes, ma'am. Wait. There it is. So yeah, check that out. And then we can talk about that if you want. I'm happy to. But like what I want to do is just on these next couple, like pre-talk about it.
Yeah.
Does that sound good?
Yeah, I'll look into this.
Awesome. And let me know.
Yeah.
And we can talk about that, whatever you want, friend.
Thank you.
Awesome. Thank you. groups.